Homework from last night, everyone. Worksheet number 17. First 4 questions are up on the board right now. Take a look at the answers. Again, we won't worry about the solutions right now. We'll do them if you had trouble with a question. Just look at the answers for 1 through 4. Five through 7. Question number 8. And questions 9 through 11. All right, let's have a look at number 8 then. It says determine the ratio of the speed of light in crown glass to the speed of light in quartz glass. We talked about this earlier in the year. Whenever you want to find a ratio, whenever you want to compare two things, okay, something like that. Compare, again, we use this analogy a bunch of times, right? Compare my age to your age. Find the ratio of my age to your age. We said it was about 2 to 1, right? How do we get that? Well, we divided my age by your age, gives us about 2. Okay, so that gives us a ratio of 2 to 1, or a comparison of 2 to 1. We want to find the ratio of the speed of light in crown glass to the speed of light in quartz glass. Then let's say it's the speed of light in crown glass divided by the speed of light in quartz glass. Let's say it's going from crown glass to quartz glass, and therefore the ratio is going to be V1 over V2. The problem is, I don't know what the speed is in either of these. I could find it. I could say N is equal to C over V. The index of refraction of crown glass is what? I think it's 1.47, or is it 1.52? I'm not sure which one's which. 1.5. Which one's which? Crown glass is 1.52. The speed of light in a vacuum is 3 times 10 to the 8 meters per second. That would give us the speed of light in crown glass. We could turn around and do the exact same thing for quartz glass. Okay, N being 1.47, 3 times 10 to the 8 meters per second. For the speed, solve for the speed of light in quartz glass, and then we could divide the two. That works, right? Everybody do that? Yes? Okay, that's perfectly fine. Okay, that works. It's a little bit more work than you have to do, okay, but it's a good, solid, legitimate method to solve the question. Here's what I did. I said, look, the ratio of V1 to V2 is the same as the ratio of N2 to N1. I know what the value of N2 is. Quartz glass is 1.47. Crown glass is 1.52. The ratio of those two is what? Whatever 1.47 divided by 1.52 is, what does that work out to be? 0.97? So the ratio is 0.97 to 1. You do it this way, you're going to get the same thing as the way that I did it. It's just that my way is just a little bit quicker. Not better, just a little bit quicker, that's all. That makes sense? Watch what happens. Just so that you understand like why they're both legitimate. Watch what happens here, okay? If I sub in this for this and this for this. V1 over V2. Well, V1 is, it's going to be C over N1. V2 is going to be C over N2. Agree with that? Right, if I just sub in the equation that I got from the index of refraction equation here for V1 and for V2, well, that's kind of an ugly looking equation, but if I simplify that a little bit, I get V1 over V2 is equal to C over N1 times N2 over C, right? Multiplied by the reciprocal. Let's cancel out the C's, and what do I end up with? N2 over N1. So in the end, we end up doing the exact same thing, right, if we do it that way. It's just a little bit longer, that's all. A little bit longer of a method. Okay. How many people did it? I got a show of hands already for the people that did it this way, okay, which is perfectly fine. Anybody think to do it the way that I did it? Yes? Yeah, and it worked out for you, obviously. Oh, you had it backwards? Okay. So you found the ratio of quartz glass to crown glass, but you had the right idea. Okay, just be careful about that, okay? That's, I mean, that's probably a fairly common mistake. We don't see a ton of questions like this, so I can't say that I've seen that mistake a million times before. But I would think you get this question on an exam, that option is going to be there if you flip them around, right? And that's probably that would probably be a relatively common mistake. I also had a request to do question number 9. Determine the critical angle for crown glass. The critical angle for crown glass. We're assuming that we're talking about air and crown glass here, right? So which way am I going? From air to crown glass or crown glass to air? Total internal reflection always happens when you're going from which medium to which medium? Right. So, yeah, right. When you're going from a slow medium to a fast medium, right? So that means in terms of the index of refraction, when you're going from a blank index of refraction to a blank index of refraction. High to low index of refraction. Good. All right, crown glass is clearly going to have the higher index of refraction. It was 1.47, or is it the 1.52? 1.52? And then, of course, air is going to have a 1.00 index of refraction. We're going from crown glass to air. We're going to say sine theta 1 over sine theta 2 equals N2 over N1. That's sine theta C, looking for the critical angle, when theta 1 is the critical angle, over, what's theta 2? What's theta 2 at the moment total internal reflection begins to occur, Josh? Anybody have that? 90 degrees, right? The angle of refraction when we've met the critical angle is going to be 90 degrees. Now, N2, always going to be the smaller number, right? Because we're always going from high to low. N2 will always be the smaller number. However, if you mix those up here, you're going to get away with it, right? Because your calculator is going to give you an error. Sine 90 is what? 1. So it becomes sine theta C equals 1.00 over 1.52. Theta C is equal to the inverse sine of 1 over 1.57. What do we get for that? Make sure you're in degree mode there, right, Tristan? 41.1 degrees, thank you. Now, what a lot of people will probably do is not even bother writing this down. What a lot of people will probably do is not even bother writing this down. Is that okay? Sure. It's always the same, right? If we come across something that's always the same way, and you want to avoid writing a couple things down like that, then that's okay. It's not a big deal. All right? I always write it down just because I want you to understand where it comes from. Okay, but if you could do it, that's fine. Good. Tristan, is that okay? All right, everyone, we get two types of curved lenses. Of course, we talked about this yesterday. This one's a what? Give me one name for it. There's two names for it, right? A converging lens, right? It's also known as a concave lens. It gets confusing, right? It does, because if I gave you a mirror that was a similar shape, at least a mirror that was thicker in the middle than it is at the edges, a convex mirror, just like we have a convex lens here, it wouldn't be a converging mirror. We have a converging lens, but this would be a diverging mirror. So it gets a little bit confusing, right? Converging sometimes goes with convex, sometimes converging goes with concave. Depends on what you've got. My suggestion would be don't memorize that. Don't memorize, okay, for lenses, converging goes with convex, and for mirrors, oh, I forget. I get it mixed up. Okay, don't try to memorize it. Look at the picture. Okay, look at the picture. If it's thicker in the middle, we know it's convex. Well, what does it do? Okay, if it's thicker in the middle, we know these rays are going to converge. If it's thicker in the middle of the mirror, we know these rays are going to diverge. Okay, let's look at it. Is it thicker in the middle? It's convex. So what's the behavior of it? What does it do? Does it cause rays to converge or diverge? Don't remember it. Look at it and think about it each time. All right, whenever we're drawing those ray diagrams for the convex lenses or the converging lenses, always two rays that we draw. First ray goes where? Top of the object where? Parallel to the principal axis. Now we said the reality is it goes to the surface, it bends, and then it bends again when it goes out the other side, right? But we don't draw it that way because it's too difficult to draw it that way. We can get the exact same effect if we just draw that lens or draw that ray of light right to the middle of the lens. And then we draw it down, straight down through the focal point on the right-hand side. Okay, again, it's the exact same effect. It ends up going to the exact same place. It's just that the path that it takes to get there is not quite the way that we have it drawn. Where's the second ray go? From the top of the object down through the center of curvature? No, there is no center of curvature, right? We call that 2F, but we don't call it the center of curvature anymore like we did with mirrors. So where does it go? It has something to do with center. Where does it go? To the optical center, yeah. Those two rays don't look to converge. In fact, they look to go away from each other. So what do we do? Sorry? Yeah, let's do the dotted lines backwards, right? It'll look something like this. Characteristics of this image. It's bigger, yeah. It's upright and it's virtual, right? Which means we can't project it onto a screen. This application, the application that's the most common for this one is what? The magnifying glass, right? Good. Okay, this one is a what? Concave lens or a diverging lens. If it was a mirror shaped like this, then it would be a concave mirror still, but it would be a diverging mirror. All right, I picked this one on purpose because we've got our object right at the focal point. If we have our object at the focal point on the other one, the convex lens, then we're going to get no image. Right? The lines are going to be parallel to each other. Let's see what we get here. First ray is, of course, going to go parallel to the principal axis, and it's going to go up away from the focal point like this. Second ray is going to go down through the optical center. Those don't converge anywhere, do they? Well, they're not parallel, so they're going to converge somewhere. If we extend them back, we find that they're going to converge right here, which means the characteristics of this image, upright, virtual, and smaller, right? Upright, virtual, and smaller. It doesn't matter what order you give me the characteristics in. Good? So what do you think is next? What do you think is next? Yesterday we spent the day drawing ray diagrams for curved lenses. What do you think comes next? This is my absolute favorite slide to have prepared probably ever in Physics 30. Why? Because all I had to do was literally go to the curved mirror math slide that I had, click Control-C, and then click Control-V, and copy it, and then change the word curved mirror math to curved lens math. It's exactly the same. It's exactly the same. The equations that we use to describe curved lenses, 1 over F is equal to 1 over DO plus 1 over DI. M is equal to HI over HO equals negative DI over DO. Not only is the slide exactly the same, the equations that I write down today are exactly the same. Except now we're not going to call it the mirror equation and the magnification equation. We're going to call it the lens equation and the magnification equation. F is the focal length, DO is the object distance, DI is the image distance, and so on. Exactly the same as it was with lenses. What about positives and negatives? Well, let's look at F, DO, and DI. When is F going to be a positive value? Well, it's going to be a positive value when we have a real focal point. And it's going to be negative when we have a virtual focal point. When's it going to be a real focal point? What type of lens produces a real focal point? What type of mirror produced a real focal point? If it was a mirror and it was converging, in other words, concave, we had a real focal point. If it's a lens and it's converging, in other words, convex, then we have a real focal point. So basically, whenever you have something that's converging, we have a real focal point. Whenever we have something that's diverging, we have a virtual focal point. It gets a little bit confusing between the lenses and the mirrors because converging focal points for lenses are from convex lenses. Converging focal points for mirrors are from concave lenses. Concave mirrors, I should say. DO. Well, DO is positive when we have a real object. And it's negative when we have a virtual object. When do we have a real object? One simple word. Always. For us, it's always going to be the case. If you go on in physics, not necessarily, but for us in physics 30, it's always going to be a real object distance. And it's never going to be virtual. So dO is always going to be a positive value, just like it was with the mirrors. DI, DI is positive when you have a real image, and DI is negative when you have a virtual image. And that depends upon, there's no real rule that we can put in brackets for that because it depends upon the particular situation that you're in. This probably seems easier this time around than it did last time around, right? Because it's the same thing. Now, there are subtle little differences, like the converging lens is convex, the converging mirror was concave, little things like that. But in the end, the general sign conventions are exactly the same. The whole thing is exactly the same as it was for mirrors. Let's look at HI, or HO, I should say, in HI. HO is positive when you have an upright object. And it's negative when you have an inverted object. HI is positive when you have an upright image. And it's negative when you have an inverted image. And finally, the last one, the magnification. When's it positive? It's almost the same as HO and HI, right? Almost. M is positive when the object and the image are on the same side as of the principal axis. In other words, if they're both right side up or they're both upside down, we're going to make M a positive value. Yep. You know what? That would be pretty rare that you'd see them both upside down, but it's possible. It's very possible. I don't know that I've seen one of those in Physics 30, but I definitely wouldn't rule it out. Although I do think it would be unlikely. It doesn't make it harder. It really doesn't make it harder if it is. It's just unusual, that's all. Yeah. Yep. Here's an example. A 2.5 centimeter high object is placed 10 centimeters from a diverging lens. A diverging lens. We want to know, A, that it's a lens, not a mirror, and we want to know, B, and perhaps more important, that it's diverging as opposed to converging. Our focal length is 5 centimeters. We want to find the image distance, the image height, and the attributes. What does that mean again, the attributes? Yeah, virtual, upright, the characteristics, right? The characteristics using the lens equation. And we want to verify it using the ray diagram. We won't bother drawing the ray diagram here because yesterday we drew all 10 possibilities. There are no more that we can draw, right? Those 10 possibilities that we drew yesterday were the only 10 possibilities that we have. So we've already drawn the ray diagram for this. Okay, this is going to be HO. This is going to be DO. This is going to be the focal length. But of course, our focal length is a negative value because it's a diverging lens. We want to find the image distance. We want to find the image height. And of course, the attributes, which we'll deal with once we have those numbers. We got two equations. You're not sure which one to start with? Guess. Okay, the worst that's going to happen is you guess the wrong one. Try the other one. In all likelihood, you're going to end up using both of them anyways. Let's say 1 over F is equal to 1 over DO plus 1 over DI. 1 over negative 5, don't forget the negative, because it's a diverging lens, is equal to 1 over DO, it's 10 centimeters, plus 1 over DI. So we're solving for DI here. Let's pull out the calculator, and let's do that little trick that I showed you when we did converging and diverging mirrors. If I can get this thing turned on. There we go. Let's say neg 5, x to the minus 1. Let's subtract from that 10, x to the minus 1. Let's flip it over, and we end up getting negative 3.33. And the units for this would be centimeters, right? Now, the final answer for that is negative 3.3 centimeters. Why do you think I wrote down negative 3.3333? Why did I write down that unrounded number? Della? I might need it for my next equation. I don't know that I will, but I got a feeling that I'm going to use it for the next one. So I'm going to write it down just in case. We always want to use that unrounded number unless it's a final answer. Okay? 3.3 is the final answer, but if I'm using that number later on, it becomes an interim answer, not a final answer. Let's say m is equal to hi over ho equals negative di over do. We don't want to find the magnification here. We don't really care what that is. We want to find hi. So let's say hi over 2.5 is equal to negative 3.3333 over do, which was 10 centimeters. What does hi become there? 3.3 times 2.5 divided by 10. Negative 0.833. Should be positive, I think, actually, shouldn't it? What is it? 546, so that is 0.833, but positive, right? Mac, do you see why it's positive? Right? Negative times a negative, right? Okay, that's important, not so much in determining how tall it is, but it's important in determining the attributes, right? The characteristics. What are the attributes here? The characteristics. Well, we know that, let's go with that one. Okay, we know since hi is a positive value, what does that tell us? Tells us what? I know. Hi is positive, tells us it's upright. Upright. In fact, we don't normally use this criteria to determine whether it's real or virtual. Usually we use di, to determine whether it's real or virtual. But if you think back to your ray diagrams, the only time we get an upright image is if it's virtual, right? So a positive value, it technically doesn't mean that it's a virtual image, but there's 100% correlation with that, right? We're going to say that since di is a negative value, then it's going to be a virtual image. And finally, larger or smaller. Well, it's 2.5 centimeters tall for the object, 0.83 for the image, so it's going to be smaller. Good. Make sense? It's the same thing, right? It's the same thing. There's a lot of places where you can make little mistakes, though. There really is, right? The whole positive and negative. If you forget the negative for the diverging lens, if you miss the whole negative 3.3, right? Little things like that. Okay, at least you don't have to worry so much about, in these ones, about being given the radius of curvature and then having to remember to divide that by 2. That doesn't happen in these ones, right? Because there is no center of curvature. All right, let's take a look at those 3 questions, please, on page 681. All right, let's have a quick look at number 3. This one, I think, throws people for a loop sometimes because of the wording of the question, but also because of the units involved in the question. It says a projector uses converging lens. That's good, okay? Converging lens just means that the focal length is positive. That makes it a little bit easier. We want to form a focused image on a screen that's 5 meters away. A focused image on a screen that's 5 meters away. What does that represent there? That's going to be di, right? Our image is 5 meters away. We want our image to be formed on this screen 5 meters away. What else do we know about the image besides where it is? It's real. If it's focused on a screen, it's got to be a real image. That means di is going to be a positive 5. Now, some of you probably never even thought of that, right? You just made it positive 5 because you didn't even think of making it negative. So you got lucky on that. Okay. I want you to be thinking about that, though. I want you to recognize that it is a real image. Therefore, it does have to be positive, not just it's positive by default. The image is generated from a slide that's located 7.5 centimeters from the lens. What's that going to be? DO, right? That's the object distance, and that's always positive. But one thing that I notice here is that One of these is in centimeters and one of these is in meters. Now, I don't care which one you use in your calculation, centimeters and meters, but you've got to be consistent. You've got to go with one or the other. We want to find the focal length here, and we want to find the magnification of the image, F and M, the magnification. Now, let's go with the focal length first, although there's no real rule on that. 1 over F is equal to 1 over DO plus 1 over DI. 1 over F is equal to 1 over 7. Let's go with centimeters. I don't know. It's easier to multiply by 100 instead of divide by 100, maybe. I don't know. Whatever you want. 7.5 centimeters plus 1 over 500 centimeters. They're both positive. So let's say 7.5 x to the minus 1 plus 500 x to the minus 1 gives me 0.135. Let's flip that over. You know what? I don't know. If this is a multiple choice question, what are the odds of 0.135 being there? Probably pretty good, right? Probably pretty good, because that's an easy thing to forget to do, is to flip it over. Let's flip that over. F is equal to 7.39. Let's write down an unrounded number in case we need that again. 0.38916. And what is that? Centimeters or meters? Centimeters. What do they have the answer in here? They have it in centimeters. Somebody asked me a question just a couple minutes ago. If it's on an exam, will they tell us what they want us to put the answer in? Yes. If it's numerical response, you always see, right, the answer expressed in scientific notation or whatever is blank centimeters or blank meters. They tell you. If it's multiple choice, well, they're going to give you 4 options. Well, you're going to see in your 4 options whether it's centimeters or meters there, right? Right. Let's round this. 7.39 centimeters now. And now let's go back and find our magnification. M is equal to negative DI over DO. In the end, this is one where I didn't actually need the unrounded number for the focal length, right? I could have got away without putting that in there, writing down the unrounded number. But I didn't know that at the time. When I wrote it down, I thought I better write down the whole number just in case. We don't have any. It was one of those things it's a good question. What other equation do we have that uses the focal length? None, 0. It's just one of those things as you're doing it, it's almost a habit more than anything, right? Okay, I'm not done the question. Maybe I'll use this number. If I thought about it, then I would have recognized, no, I don't have any other equations of focal length. Of course I'm not going to use that number. But in the end, I'd rather sometimes do a little bit more just because I'm not thinking than do less because I'm not thinking, right? So negative DI is negative 500 centimeters over DO, which is 7.5 centimeters. That's going to give me 66. Make 66.7? Yes. We're not asked to find the characteristics here, but we could do it, right? What are the characteristics? Larger, smaller, same size. A lot bigger, right? I mean, logically, you got a projector here, right? An LCD projector. You can't see the object inside that projector, but you know it's got to be smaller than the image that's formed on that screen, right? You know it has to be. You look at the magnification, it's 66 times bigger. Okay, of course it's going to be bigger. Is it right side up or upside down? Yeah, it's upside down. At least it's upside down relative to the object, right? If the object is upside down, then the image will be right side up. But it's flipped over relative to the object. And is it real or virtual? It's real. We don't even need a number for that. We're told that it's focused on a screen. It's 5 meters away. Make sense? All right. Some questions on page 683 that I'd like you to do, please. 683, number 1 to 2. And numbers 8 to 20. You know what? We've got about 15 minutes here. I'm going to give you a chance to work on these now. Okay, we're not going to go any further with it. Okay. That's the good news. The bad news is you're going to have a little bit more work to do as well, but it's all going to be It's all going to be for Thursday. Okay, for Thursday. So this plus worksheet number 18. This plus worksheet number 18 for Thursday. Okay? You may have an opportunity for a little while tomorrow to work on worksheet number 18 in class. I'm not sure about that yet, so don't bank on it. But let's at least try to get these check and reflect questions done today in class so you have a little bit less to do at least, okay?